if I look at the covariance of a random variable with itself, what happens? So what is the covariance of a random variable with itself? It is basically equal to the variance of that random variable. So covariance of x and x itself is going to be expected value of x times x minus the product of individual expectations, expectation value of x times expectation value of x, and that is basically the definition of the variance. Okay, so the covariance of a random variable with itself is equal to the variance. Okay, now let's give a proposition. Let's just say a is a real number. A is a real number, it's a constant value, it is not random. What is the covariance of ax and y? So there is a multiplier in front of x. So what is the covariance? How this covariance changes? Now, any coefficient inside the covariance, either in front of x or in front of y, it doesn't matter, can get out of the covariance without any change. So that a value here can get out of the covariance, and the proof is very simple. You know, the covariance of ax and y is what? Expected value of the product of these two random values, ax times y, minus the expected value of ax times expected value of y. Now, both a values in these expectations can get out of the expectations, and a here becomes a common multiplier, and the remaining terms gives us the covariance of x and y. So unlikely to the variance and likely to the expectation, the coefficients inside the covariance can get out of that covariance without any change as a multiplier. Let's just generalize this situation. For example, if we have two arbitrary real numbers, a and b, then the covariance of ax and by is going to be a times b times covariance between x and y. So both of the coefficients can get out as a multiplier. So this is an important property about covariance, unlikely to the variance, but likely to the expectation. The coefficients in front of the random variables can get out without any sign change or without any function. They get out of the covariance as a multiplier. Now here we will have something different. So let's just say we have a sequence of random variables xi, and then we have another sequence of random variables yj. So we have the first sequence that consists of m random variables, and the second sequence yj of n random variables. Okay, so what is the covariance between the sum of the first sequence and the sum of the second sequence? So what is the covariance between the sum of the first sequence, because it is going to be a random value as well. It is going to be a sum of random values. It is going to be random. What is the covariance between the first sum and the second sum? Now that covariance, my friends, is equal to the sum of individual covariances between xi and yj. So for all dual combinations, I calculate the covariance of x1 and y1, x1 and y2, x1 and y3 until x1 and yn. Then I skip to x2. I calculate the covariance between x2 and y1, x2 and y2, x2 and y3, so on and so forth. And I skip to x3, x4, so on and so forth. So for all dual combinations, I calculate the covariance of dual combinations and sum them up with a double summation as I changes from 1 to m and j changes from 1 to n. Okay, just like multiplication. So if you multiply some of these values with the sum of these values, you are basically multiplying each dual combination with each other and sum these dual combination products, right? So just like that, here we have the covariance of the sum of two random variable sequences that is going to be equal to the sum of all dual covariance of all dual combinations. Now, let's prove that. Let's see if this is true or not. And in order to see if this is true or not, I'm going to use the classical formulation of the covariance. So according to the classical formulation of the covariance, that is going to be equal to the expected value of the deviation of the sum of xi values from its expectation So I say in parentheses, the sum of xi values minus the expected value of the sum of xi's times the deviation of the summation of yj values from their mean. So which is the sum of yj values minus the expected value of the sum of yj values. Now, what I'm going to do with the interior expectations here and here, we have the expected value of sum of random variables, right? Which is going to be equal to the sum of individual expectations, both here and here. Now, after doing that, you will realize that you have summation of xi over I index, and with the same index, you have the summation of expected value of xi's, which can be rewritten as a summation of the deviations. And you can do the same for these deviations as well. You can write the summation of deviations. And since we are multiplying the components which are summed here and the components which are summed here, instead of that, I will multiply each component with each other with dual combinations and run a double summation. And then the summations we can get out of the expectation, the outer expectation, and inside you are going to see the covariance between every dual combination among these random variables. So the covariance between the sum of two random sequences is equal to the summation of the covariance of all dual combinations within these sequences.